Welcome, everyone. For today's prep, we're going to start looking at applied optimization. So we're going to take what we learned in 04, our constrained optimization, kind of the general strategy on the calculus of solving these types of optimization problems, and we're going to put them into a more applied setting. So really, we're going to be developing a mathematical model for a kind of a word problem. And then from there, we're going to use our derivatives to figure out where we have a max or a min. All right, so we're going to look at an example here. We're going to look at example 1. And again, we kind of have our steps listed out here for constrained optimization. First, we want to figure out the objective and constraint equations. And then we'll solve the constraint equation for one of the variables. We'll plug that into the objective. And then we optimize the resulting function, so finding and classifying the critical numbers. So all those steps are going to be the same. The difference here is we don't have the functions to begin with. We're going to have to figure those out. All right, so let's look at the problem. Let's read through this. So we want to plant a rectangular garden along one side of a house, and we're going to fence in the other 3 sides. And what we want to do is we want to find the dimensions of the largest garden that can be enclosed using 40 feet of fencing. All right, so for these applied optimizations, if they're kind of geometric in nature, so right away, it kind of stands out to me, we have a rectangle. It's usually helpful to draw a diagram. So I would almost consider that like a step 0. For these kind of geometric ones. All right, so we're going to plant a rectangular garden. So let's draw a rectangle. And we're going to put this along one side of a house. So we could just pick a side, doesn't matter which one. So let's say our house is over here. So here's the house. And here's our garden that we're going to be planting. All right, got a lot of nice greens in there. All right, so what we're going to do is we're going to fence in. We're going to fence in the 3 other sides. So we don't have to put a fence along this side because our house is there, but we are going to fence in the 3 other sides. All right. So we got our fence, we got our garden, and now we need to start figuring out the 2 equations. So again, we want to remember, what is the objective? So the objective equation is the thing that we want to maximize or minimize. So if we go through the wording of the problem, we're looking for words like maximum or minimum or smallest or largest. And in this case, we see that right here. We want the largest garden. So the way we measure the size of a garden, that's important for kind of planning things, is with area. So the objective is going to be the area. All right. And to kind of shorten things up, let's just call this A. All right, so we want the area of our garden. So far we don't have any, we have our diagram, but we don't have any variables. So usually we want to introduce some variables. And so for a rectangle, there's 2 dimensions. So let's call this one X and this one Y. So the area of this rectangle is just length times width. So it's X times Y in this case. All right, so this is our objective. That's our objective quantity. That's the thing we want to maximize or minimize. Now the constraint, this is something that puts a limitation on how big our garden can be. And the limitation in this case is, well, we only have 40 feet of fencing to work with. So we can't make this garden as huge as we want because we only have 40 feet of fencing. So our constraint is going to be the amount of fencing. All right, so how much fencing? So let's think about how much fencing it would take to fence in this side right here. Well, y represents the length, so it would take y amount of fencing for that side. And then x is the length of this side, so that would take x amount of fencing. So it would take y plus x, and then the amount of fencing over here, this also has dimension y. So it's going to take y plus x plus y, and we have 40 feet to work with. So we want the amount of fence there to be really as big as possible. So we're going to use all the fencing, so 40. All right, so this is our constraint, and this is our objective. So let's solve our constraint equation for one of the variables. And in this case, it's slightly easier to solve for x because we have only one x. And maybe we really clean this up a little bit. So we have 2 copies of y. Let's add those together before we do anything. So we could rewrite this before doing anything else as 2y plus x. We have 2 copies of y there. All right, so let's rewrite this constraint equation. And we're going to solve it for x. Slightly easier to solve for x. We don't have to divide by 2. If we were going to solve for y, we'd have to divide by 2, and that would get some fractions. So in this case, slightly easier to solve for x. And when we do that, we get 40 minus 2y. And then step 3 is we're going to take this, what we solved for in our constraint, and we're going to plug it into our objective. So our objective is a equal to x times y. And I solve for x, so wherever I see that in my equation there, I'm going to replace that with what we just figured out. So our area formula is going to be 40 minus 2y times y. And we're going to, in the next step, we're going to be doing derivatives and whatnot, so usually helpful if you can do the multiplication here. So when we distribute, we get 40y minus 2y squared. All right, so this is our objective function now that's in one variable. So we're ready to do our optimization. So the way we optimize, the first step is we want to get the critical numbers. So we got to find our critical numbers first. And then once we have our critical numbers, the second part of this is classify them. Make sure that we're getting a max or a min. All right, so let's find our critical numbers. So we're going to calculate the derivative. So we'll call this a prime. And if we differentiate, we get 40 minus 4y. And then we look for where the derivative is equal to 0. So when we do that, we set our derivative equal to 0. And when we solve that, we get y is equal to 10. And then we also, sometimes this happens. We've seen it before. We also, for our critical numbers, need to look for where the derivative is undefined. But in our case here, our derivative doesn't have any division, so we're okay. So there's no critical number from this. All right, so we found our critical number. There it is, y equals 10. And we just want to make sure, do we have a max or a min there? We want to classify it. And when we classify our critical number, we have 2 tests. We have the first derivative test or the second derivative test. Usually second derivative test is a little bit easier. So we're just going to state the name that we're using. So second derivative test. That means we need to calculate our second derivative. So our second derivative here is -4. So we're just differentiating 40 minus 4y. Derivative of 40 is 0. And then derivative of -4y is just -4. And the way we do our second derivative test is we take our critical number, which was y equals 10, and we plug it into our second derivative. And in this case, our second derivative, when we plug 10 in, Well, our second derivative is constant, so no matter what you plug in, you always get -4 out. So we get -4. And so to remember what the second derivative test tells us, it's negative, means concave down, draw the shape, draw the shape. Well, still not great, but we can tell it's a max. And if we go back up to the wording of the problem, let's see. We only found one critical number, so if we're going to have a high point, this is the only place it can happen. So let's just go back up and check. What was the problem asking for? We wanted to find the dimensions for the largest garden. So we found that it was a maximum, so that checks out. We wanted to find the maximum, and we did find the maximum. Now we just want to make sure, the last step for this is we just want to make sure we actually answer the question. So the question's actually asking for the dimensions of our largest garden. So we only have the y value here. We also want to find the x value. And in our case, units are given, so we want to make sure that units are in our answer as well. So when we actually answer the question for these applied optimization ones, double check. Make sure if there's units given in the problem, your answer should include units. And our units here are feet. So we already found that y is equal to 10 feet. And we want to figure out x. So we have a few options to figure out x. We could go back directly to our constraint equation, figure out x that way. But we already have this version where we actually solve for x. So let's just plug in there. So x is 40 minus 2, and we're going to fill in our y value, which is 10. And this ends up being 20. So the units for x are 20 feet. And if we go kind of a sanity check, if we go up to our problem, we found that the y value here was 10 and the x value was 20. It makes sense then that this side is longer because we kind of have a discount on that side. We get this other side for free. So it makes sense that the side of our rectangle that's bigger has this kind of discount alongside the house. All right, so this is really the idea here. And most of the work is very similar to what we saw with the constrained optimization. Very similar workflow here. The thing that's new is we have to interpret the word problem. And usually doing a diagram helps with that. And then we have to come up with these equations. So they're not just given to us. All right, so we'll see some more problems like this in class. So we'll see you then. Bye-bye.